Good morning. I'm ANLIN, that's Kevin, and that's RACHANA. Thank you for the opportunity to present our work. Our research project is titled Epidemic Dynamics on Symmetric Networks. In the last several months, we have been investigating how epidemics behave on certain random and non-random networks. Our overall goal is to study epidemic outbreaks on random and non-random networks by taking into account the symmetries of the social groups considered. For example, in a family or classroom, it's highly likely that all individuals are connected to each other. To incorporate these appearances of highly connected clusters of individuals, we introduced two novel types of networks and study outbreaks on them. First, the regular D-clique tree graph, which is a non-random network, and second, M-graphs, which are random networks. We model a network of individuals through graphs, which are a set of vertices and edges. Vertices denote individuals, and an edge connects two vertices and thus represents a possible path of infection. We consider two approaches to epidemics on contact networks, both of which depend on P-inf, an individual's probability of infection, and P-rec, an individual's probability of recovery. In the next generation model, both P-inf and P-rec are set to 1, which means that all individuals in the network will get infected and eventually recover. In the general discrete time model, it is possible for P-inf and P-rec to be less than 1. Our driving question is, how do clusters of completely connected individuals, known as cliques, influence epidemic outbreaks? In what follows, we will answer this question in both the terms of non-random and random networks, starting with the non-random ones. We build off the work done by Schaposnik and Calendar. Last year, they considered epidemics on D-array trees. These are networks given by a rooted tree in which each node has at most D children. It depends on the degree D and the height lambda, where the degree D refers to how many edges are connected to each node, and the height lambda refers to the maximum distance between the root vertex and any other vertex in the graph. They use the IONTW platform to analyze dependence on these parameters and obtain formulas for P sub I of an outbreak lasting I time units, for when I is 1 or 2. We have reformulated our driving question in the terms of non-random networks. How can we adapt this model to encode outbreaks originating, for example, within a classroom, and then reaching a broader population via transmission via schools? To incorporate completely connected clusters of individuals, we introduce a new type of network. We call our network the D-clique tree graph, denoted by A sub D of lambda. As shown in the figure here, we add the light blue edges to the regular tree graph to form cliques. It is a regular tree graph of degree D and height lambda with added edges to form D cliques on the terminal vertices. In a clique, each pair of vertices is connected by an edge and thus models families or classes better. The body of A sub D of lambda is a set of vertices which are not in any clique. In this network shown here, it is the bottom right vertex, and in this case, it coincides with the root vertex. We calculated network properties that determine an outbreak's duration. Using mathematical induction, we calculated the number of cliques and the number of edges in A sub D of lambda. Note that as the degree D increases, both the number of edges and cliques increase exponentially. This shows that for even a slight change in the network structure, it can have huge impacts on the scope of the infection and the outbreak duration.
Another property of interest is N sub R, the number of vertices at fixed distance R from the index, or source of infection. In other words, it is the number of new people infected when the pathogen travels R steps. We have found a formula for N sub R and used it to construct the following figures. Note that N sub R is exponential in R, and furthermore, as D increases, so does the steepness of the curve. The exponential behavior means that when an outbreak occurs, it will spread very quickly. We can also analyze the average outbreak duration, the amount of time until the last infected person recovers, at which point the outbreak dies. We could compare our model with the Schaposnik calendar model, assuming the outbreak starts in an outermost vertex. In figure A, in our model, we see that an increase in recovery probability leads to a longer outbreak. However, in the Schaposnik calendar model in figure B, the opposite is true. An increase in P-rec leads to a shorter outbreak. Thus, the two models differ in their predictions of outbreak duration in terms of P-rec. We can also compare the values of P sub 2, the probability that the outbreak dies within 2 time units, where P-rec is set to 1. In figure A, we compare a 4-array tree with a 4-clique tree that we studied. And we noticed that for most infection probabilities, P sub 2 is higher for our model than for the Chabot calendar model. A similar result holds true in figure B, where we compare a 4-array tree, a 4-regular tree, and our A sub 4 of lambda. Here, still we have that P sub 2 is higher for our model than for the other 2 models. Thus, the probability that the outbreak lasts more than 2 time units will be much less for our model. We can illustrate this quantitatively by dividing P sub 2 for our model by P sub 2 for the D-array tree model, where we set P-rec equals 1 again. Note that when the infection probability is low, such as 20%, we see, as modeled by the black line, we see the ratio is close to 1, which means P sub 2 is similar in value for the 2 models. However, once we increase infection probability to 50%, as shown by the blue line, then we see that P sub 2 becomes up to 100 times greater in our model than in the Chabot calendar model.
Now that we have considered epidemic outbreaks on non-random networks, let us consider epidemic outbreaks on random networks. In order to do so, we use the radograph, since every random graph generated using the Erdős-Rényi model is isomorphic to the radograph by the graph extension property. Therefore, in studying the radograph, we're effectively studying all of these random graphs. The radograph is generated by labeling vertices in the network with primes congruent to 1 mod 4 and putting an edge between 2 primes P and Q if one is a quadratic residue modulo the other. Here we've illustrated the graph for the 9 smallest such primes. Our driving questions remain the same as before. How do cliques influence epidemic outbreaks in random networks? And how do we account for relationships between individuals? First, we consider the appearance of cliques. In order to do so, we proved that the radograph is connected and that even more so, any 2 vertices are at most a distance 2 apart. This then led us to proving that any n random vertices have a probability of 2 to the negative n choose 2 of forming an n clique. This is an important step in estimating clusters of different sizes in the network. Additionally, we also noticed the appearance within radographs of networks previously studied. Indeed, for any vertex, there's a degree d and a height lambda such that the vertex is the root of a sub d of lambda. In other words, if the root of the graph is infected, then the infection will spread like how it would on a d-clique tree graph. This will help us apply these results in the future on a sub d of lambda. As we mentioned before, we also wanted to understand how to add conditions reflecting relationships. Therefore, we introduce a new type of network depending on a multiplier function m. Here, 2 primes P and Q are connected if Q is less than or equal to P times m of P, where m of P is the multiplier function. For the particular multiplier m of x equals 1 plus c over x to the alpha, we prove that the frog model, which models the spread of a pathogen, is such that the pathogen returns back to the origin in finite time. Here we've illustrated the graph of P times m of P for different values of alpha and c, where alpha and c are constants. As you can see from the definition, we're using P times m of P to realize which vertices are connected, and that, in particular, the larger the value of P times m of P, the more values of Q are allowed. We adapted our previous definition to introduce quasi-M radographs, where the vertices are now primes congruent to 1 mod 4. We further add a reciprocity condition to introduce M radographs, but keep the multiplier constraint in order to model a more real-world scenario. For example, a civilian in India or China has a very low probability of infecting someone in the US due to their limited interaction. But 2 people going to the same school have a very high probability of infecting each other because of their numerous interactions. The multiplier function better allows us to model this feature of the real-life spread of infections. As you can see from the illustration, we have to erase edges, the red ones, from the radograph in order to form the M radograph. This makes the M radograph more constricted, making it less connected, and thus models real life better. Proving connectivity for these networks is a much harder question, but at the moment we can show that it is equivalent to proving the conjecture which is stated here. As you can see from the conjecture, we have effectively turned a graph theory problem into a number theory problem. Now that we are nearing the end of our presentation, let us go over what we've done so far and what we hope to do in the future. In order to study outbreaks in networks with completely connected clusters of individuals, such as classrooms, we introduced two new types of networks and studied their properties as well as the outbreak's characteristics. In the future, we hope to extend our work in many ways, one of which includes studying safe zones, areas of the network with very low probability of infection. This is similar to a quarantine in real life. Additionally, we'd like to prove connectivity for the M radiograph by proving the conjecture which we stated on the previous slide. Proving this would also allow us to find a lower bound for the number of cliques of a given size. We would sincerely like to thank everyone on this side, especially the Siemens Foundation for giving us this unique opportunity, and George Washington University for hosting the 2017 National Finals, and also to our esteemed judges for listening to our presentation here today. Thank you for your time and attention.